Trust Cloud Native Security. So first, a little bit about me and my background. I'm currently a software engineer at Solo on the Glue Gateway team. So that's our Kubernetes Gateway API Envoy-based gateway. But I'm also involved in the Kubernetes community. So I'm a CNCF ambassador. I've been on the release team since 127. In that time, I've been the enhancements lead, the 131 release notes lead, and I'm actually currently the one of the release lead shadows for 132. But today we're going to talk about cloud native security. And I think it's good to have a little background on what challenges exist specifically for cloud native and how it's different to other environments. So the first thing that comes to mind is the dynamic environments that you're in. So there's frequent infrastructure changes. Your workloads are ephemeral. So you might have like an auto scaling policy in place. That means your workloads are coming up and down. And that kind of feeds into how you're adapting your security policies. As things come up and down, you need your security policies to also be dynamic. The second thing is containers are a thing. So containers bring a new attack surface, including vulnerabilities in the images, the runtime environment, and different orchestrator exploits that exist. And then the third thing that I think is slightly different in this environment is how identities are managed. So in traditional security, you might rely on a static identity like a network IP, but you can't really do that in a cloud native workload because, again, they're ephemeral, they're very dynamic. So you need to use dynamic identities like spiffy IDs to establish trust. And that's what enables workload level access control, secure communication, and all of that stuff in dynamical changing environments. So there's kind of three phases to developing a cloud native app, and all of these three phases have their own security challenges. So the first phase is when you're actually building the application. You might want to have plugins in your IDE to do like security checks. You want to make sure you're treating all your infrastructure changes as code. So you're not changing security settings in a web UI. You have like a record of every change you made. You want to make sure you're using a supply chain manager to know what you're pulling in to your code base. And then you also want to have like different security scans in place, so like static analysis that just analyzes your code to see if you're using best practices, vulnerability scanning to make sure you're keeping up to date with CVEs, and like workload manifest scans, so like making sure your Kubernetes manifest files are using best security practices. So all of that is kind of in the develop phase. Then it's the distribute phase. So that's like when you actually build your app, like how you distribute it to the world. Like where is your build pipeline running? Like is it an isolated continuous integration environment? Are you still doing image scanning? So you're identifying vulnerabilities in the images you're building on top of. And then also image hardening, so like making sure that you're restricting access, like restricting what execution can be run in your images. So those two phases are like happen, before you actually run the application. But there's also the runtime phase. So when you've built your app, you've distributed it to the world, like now people are actually running it. So, you want to think about like where the app's actually running. Is the cloud environment that it's running in secure? Is the infrastructure config you have in place secure? Now it's the question of like workload orchestration, like what has, access to your control plane. So what can spin up new pods and whatnot? Are you monitoring and detecting changes that are happening in your environment? Are you enforcing, the principle of least privilege for any API interactions you have? And then in the application itself, like who is your application talking to? Are you limiting the network connections to only the necessary endpoints? So all three of these are important, but in this talk, I'm going to focus on zero trust in the aspect of the cloud native runtime security. So this is from the CNCF security white paper that was published a couple of years ago. I've included the link there. It's a really interesting read. You should check it out. But in the runtime security phase, there's a lot of things that, kind of fit into this phase. So like I mentioned, like the policies, the secret management, where you're pulling your images from. And it kind of feeds into the question of like, okay, if you've made sure your distribute phase and your develop phase are secure, can you assume that everything in your Kubernetes cluster is secure? So if I have a bunch of applications that I develop that I know are secure, if I have my kube server or API server, like why can't I assume my cluster is a secure environment? And the reason for that is like if something goes wrong, what is the blast radius of that? And one example that happened a couple years ago, which has a pretty funny name called Drupal Geddon 2. This was a pretty big critical CVE in the Drupal open source content management project. This allowed attackers to compromise not only the application itself, but like it was a remote code execution vulnerability. So depending on how you set up your cluster, they could compromise the container, the pod, or even the Kubernetes environment and spin up like crypto mining workloads to mine crypto in your cluster and use your compute for free. So given that vulnerability, one of the things that you could do to avoid vulnerabilities like this is network segmentation. So you're going to restrict access of critical components to only what they need. In a Kubernetes cluster environment, you can use RBAC and network policies to minimize the impact. Again, so like only your app has only certain permissions to do certain things. And then the last thing is being proactive with best security practices. And the best security practice we're going to focus today is zero trust. So zero trust is not just a buzzword. It's actually like a way to avoid things like the Drupal Geddon attack. Because it's a principle or like framework when designing your system that you always want to assume that no workload inside or outside is going to be trusted by default. So it like boils down to this like cute little saying, you're never trusting anything, you're always verifying. And it's been, recommended like in the white paper I mentioned that the CNCF put out for the security tag, and then also like more recently the executive order on improving the nation's cybersecurity in the U.S. Had an explicit reference to it as a recommendation. As people move to the cloud, they should be adopting zero trust architecture. Like what it boils down to is what we saw on the previous slide is you're implementing the principle of least privilege. So you're going to assume that breaches do happen, but if they do happen, you're going to limit the blast radius of what can go wrong if they do. So that minimizes an attacker's ability to move through your network undetected because they only have certain permissions that they've gone through the exploit. So they don't have access to everything in the cluster. So in order to do that, you kind of need three things. The first thing is identity verification. So in your system, each entity needs to be able to provide verifiable proof it is who it says it is. The second thing you need is a means of independent authentication. So each entity needs to be able to authenticate with a trusted third party using some kind of decentralized mechanism. We're going to take a look at PKI. And then the third one is you want secure communication. So once you've like established your identity, once you've verified the identity, you want to make sure all communication that happens between two entities in the system are confidential and tamper-proof. So you need to establish that once the identities are established. So the first thing we're going to take a look at is how you establish identity. So in a lot of cloud native systems, you're going to be using a digital certificate. So it's just a document that identifies an entity like a server or client by linking it to a public key and all the certificate information that you need to know about the entity. So a certificate can have things like the public key of the entity. So like mybank.com's public key. You can use that to verify that that cert is who by checking the cert was signed with you can use the public key to verify that the cert was signed correctly, right? It'll also have the common name, so the DNS of my server, for example, like mybank.com, contact info for the organization, like where the organization is based, the validity date, so like how long the cert is valid for, the URL for revocation. So like if something is wrong with the cert, you want to check that has it been revoked or not. And then you also need the public key. So the cert info and the public key get combined into a CSR, which is a certificate signing request. That CSR goes to a certificate authority, a CA, and then the CA signs the cert with its private key. So then anyone in the system can use the CA's public key to validate that the cert is actually signed by a valid third party. So this is the kind of the independent authentication stage. So if I have a client and server, when the server asks the CA for the cert, we looked at that path in the previous slide. So it has the public key and the identifying information. And then when the client connects to the server will present its cert, and then the client can use the trusted CA to validate that the server is who it says it is. So once you have the identity and the independent authentication, then you can get to the secure communication phase. So this is an example of MTLS because both parties, the client and the server, are mutually presenting certs and validating them. But the initial part is that TLS handshake. So the client and the server propose a crypto to use. They present the certs, they validate the certs, and then everything after that is securely transferred. So the initial handshake actually isn't encrypted. It just is the initial communication to make sure that both entities have validated that they are who they say they are. They've agreed on how they're going to communicate. And then after that, all of the data going forward is going to be encrypted. So this is kind of like, the basic flow of any MTLS connection that you have. So now we're actually going to do a demo. I'm going to show MTLS the hard way, where in a Kubernetes cluster, I'm going to use K3 Ds to spin up a cluster. We're going to create an identity for our client and server and show how to do everything manually. This is actually based on a demo Lin Sun from Solo, our head of open source, gave at Cloud Native Security Con, which I thought was really cool. But we're going to dive a little deeper into how it works behind the scenes. I have included the QR code there, but you can also check out my fork of her repo on my GitHub. And yeah, let's take a look. So I've already actually spun up the first setup environment script. So I have a Kubernetes cluster already running locally. We can take a look at that in K9s. So in K9s, I have Istio installed, but we're not really going to use that yet. We have Kiali, we have Prometheus, again, not really using that yet, but we don't really have any services in the default namespace. There's nothing really installed other than the basic setup. So the first thing I'm going to do is show a very simple client and server. So the server I'm going to use is a node server that I'm going to build, or I've built already. And it's just listening on HTTP. It's going to respond happy Navarathi, and it's listening on port 3000. So I have a simple Docker file that takes that and builds it. And then my manifest files have a service account, a service, the Kubernetes service that has port 3000 again, and a deployment. So this is my simple deployment image that I'm going to use. Again, there's no certs, there's no encryption. It's very simple, not very secure. And then on the client side, I kind of have the same thing. I have a service account, a service for my client, and then I'm just using the curl container image to be able to send requests to my server. So if I go back to my my README, the first step, I'm going to apply those two configs. It's in the simple folder. Yep. So I applied the two YAML files I had, and you can see that this is hard to see. These just spun up, so I have my client and server. They're 12 seconds old. So now I can actually send some traffic. So we're gonna kubectl exec into the client and then send a curl request to the server. So they're all in the default namespace, so I can just use the server as the host name here. Cool. So I ended up using the -v flag to get some extra info, but you can see that there's no TLS handshake. It's just using HTTP, but I do get a 200 response and a happy Navarathi message. So very simple, very insecure. Let's try to add MTLS to this. So in order to do MTLS, we kind of saw the steps you need, right? You need your private key, you need your CSR, and you need your cert. So we're going to use self-signed certs for this demo. Not very secure, but it's a simple demo. So the first thing I'm going to do is use OpenSSL to generate a key. And I'm going to use the hello passphrase just because it's easy, again, for demo purposes. And then once I've generated the key, I'm going to use that key to generate the CSR. So remember from the slide, we need a bunch of cert info and the private key to do the CSR request. So when I run this, again, the password is hello. This is where it's going to prompt me to fill out a bunch of info about where my client and server live. So for the server, I'm based in the US. I'm going to put US down. I live in Massachusetts. I'm going to do Massachusetts. In Cambridge, so I'm going to put Cambridge down. I work for Solo. I'm going to put Solo down. We're going to skip the unit name, the common name. So, okay, this is important. We need to make sure the common name matches what our FQDN is in Kubernetes. So again, it's running in the default namespace, but the deployment is going to have, or the service is going to have MTLS server as the name. So we just need to make sure that matches. And then I'm going to skip the email, I'm going to skip the challenge password, very secure. And that was it. Now we have our CSR file. So the last step is we actually need to go to a certificate authority. In this case, it's just going to be a self-signed cert to get a real cert file output. So I'm going to, again, use OpenSSL to do that. I'm going to make it expire in 365 days. So it's going to be a year-long cert. And again, I need my private key file, and that outputs the server cert that I'm going to use. So that was kind of a walkthrough of the slides that we looked at earlier, where we've actually generated our own cert. Again, it's self-signed. It's not like what you would use in the real world, but it will work for demo purposes. And then I've actually done this already for the client, but you do the same thing. So you need to generate a separate key for the client. Then you need to, make a CSR request for the client with that key, fill in the same information. So like, country, like all the identify information. And then finally, you generate the cert itself. So now that we have our certs, we can take a look at how we have to change our node server to do some surgery on it to actually use those certs. So if you remember, the node server from before was super simple, using HTTP, no options here. This new server is going to be a little more complicated because we need to actually provide our certs. So if I look at the JavaScript code here, what I'm doing is I'm adding the server key. So this is going to encrypt our communication going forward. I'm adding the server cert. So this is what we're going to use to verify the server's identity from the client side. And then the CA. So this is the cert the server can trust. And this is going to ensure that only the client is going to be able to talk to our server. The other important thing that we have to set here in the options is request cert to be true. So this is saying that the client has to present the cert before communication can happen. So this is what's enabling MTLS in this case. And then the passphrase, you might see it's familiar. I just generated all the keys with hello. So this is what I'm going to use here. Okay, and then the last little change is you'll notice that this is now using HTTPS, not HTTP, but the port's the same. Cool. And then in the Docker file, in order to build this, we had to copy over a bunch of certs. So we're just copying all the certs that are in the server file to actually be able to use them. And yeah, that's about it. And then on the client side, kind of very similar, we're still using the curl image, but we're going to copy over the certs that we have in order to be able to present them to the server when we send our curl request. Cool. Okay, so then let's look at the manifest files. So in the manifest files, we're changing the name everywhere to be MTLS client to make it clear the difference between the two. So MTLS service account, MTLS service. Again, this is all for the client. And then the biggest difference is instead of using the curl client directly, I built a new curl client with the Docker file we looked at earlier, tagged manual MTLS. So this curl client is going to use that Docker container instead, Docker image instead. And then on the server side, again, very similar. We're just changing the name everywhere to be MTLS server. And then in the image, we're going to use the manual MTLS image that we looked at. That's using the secure, not this one, this version of the node server. Cool. So let's apply those configs. So we already looked at the certs. Let's try to look at, try to apply this first. Oh, sorry, wrong repo, manual MTLS. Okay, so I did a kubectl apply to the two manifest files we looked at. It created all the stuff. If we look at K9s again, we should have our old client, it's been up for like a minute, and then our new MTLS client and MTLS server. So they're all running in the default namespace, but these are the new pods that got spun up. Cool. Okay, so now we have to send some traffic and see if everything worked. So I'm going to send, similar to before, I'm going to exec into the MTLS client this time, and then send a curl request with no cert and see what happens. So I'm going to make this a little bigger. You can see that without a cert, we failed. So curl didn't fail to verify the legitimacy. We can establish a secure connection, so the connection terminated. Now let's do the same thing, but with our certs provided. So again, going from the MTLS client to the MTLS server, same port as before, but now I'm providing the certs. So I'm providing the client cert. This is who I am. This is the CA cert, because again, they're all self-signed, and the client key to do encryption after the handshake. So once I send that, actually, let me add the -v flag so we can see the TLS handshake going on. So yeah, a lot more content now. So with the -v flag, you can see that the TL handshake happens. So our client says hello, our server says hello back. They decide on a crypto, and then we verify both the client and the server certs. So you can see there's two verification steps that happen. And then once the handshake finishes and we've decided on our crypto, then everything going forward is secure. So our Happy Navarathi message was securely encrypted with MTLS, or securely encrypted, and the communication was over MTLS. So that was a lot of work. We had to generate the certs manually. You can imagine in like a year, once the certs expire, we have to go in, rotate the certs manually. We had to do surgery on our little JavaScript app, which, as the application developer, I really probably shouldn't be, manually implementing MTLS. I should really be focused on what the application does. So it was a lot of work just to get basic client server MTLS working, and it feels like there should be a better way. We know zero trust is important. We know we need to be able to restrict, who's talking to whom, and also have secure communication. But it does seem like a lot of work having to implement this per application everywhere. So the good news is there is a better way. So if you looked at the cluster I had earlier, it kind of gave you a hint. We're going to be using a service mesh to add the same MTLS as before, but with less headache and less steps. So there's actually going to be a great talk on service mesh coming up as part of the series that you should check out. So I'm only going to touch the surface level service mesh aspects and focus specifically on security. But a service mesh, for those that don't know, is a programmable infrastructure layer that manages communication in your microservice architecture. So it's usually divided into a control plane where all the policy lives, and then the data plane where you have often a sidecar injected into your workload. And then all traffic is captured, goes through that sidecar, and that sidecar has the config that's been sent over from the data plane, the control plane to the data plane. So I'm going to look at, there's, again, like I mentioned from the previous slide, there's 3 aspects, like traffic management, so how you're shaping the traffic, like where it's going to, retries, timeouts, fault injection, canary deployments, like traffic mirroring, load balancing. That all is things that a service mesh can do, but we're not going to focus on today. Another reason people use service meshes is for the observability. So they provide like a way to get centralized metrics, so you don't have to implement your metrics collection at the per application level. You're getting networking metrics from your service mesh. You get logs, distributed tracing, and other things. We're going to briefly look at this, but more from the security standpoint of like how the connection is getting sent. And then finally, security. So the control plane is providing identity-based access control, in our case with SPIFFE IDs, and end-to-end encryption with MTLS. Because you have this extra layer, your workload itself doesn't have to implement anything. You have your sidecar or proxy implementing the identity and like cert rotation and MTLS between everything in your data plane. So I'm going to take a look at specifically Istio. There's a lot of service meshes out there. Like Linkerd is another great project that's graduated with the CNCF. But a lot of my background is in Istio, so I'm going to show how to do it with Istio. In classic Istio in sidecar mode, you have, again, your control plane where Istio-D is the deployment that configures all of the Envoy sidecars in the data plane. So this is where, like, if you are a user and you write like an authorization policy, Istio-D will take that authorization policy, translate it into something Envoy can understand for a specific workload, and then that policy will be applied for that like proxy that's injected into the workload. So in the sidecar sense, identity is managed when the Istio agent, which is part of that sidecar, reaches out to Istio-D with a CSR request, so the certificate signing request we looked at earlier. Istio-D, the control plane, is responsible for generating the signed certs. So it returns a signed cert, and then the Istio agent is running SDS, so it provides the cert and private key to the Envoy proxy. And then in Istio, you can have MTLS for free because they have this feature called auto MTLS. So based on the transport socket match in Envoy, it either matches the TLS mode enabled or TLS mode disabled, and it'll use the cert that the agent got to do secure MTLS communication. So this is pretty nice because Istio is like responsible for all like the cert rotation, all of that, and you don't have to change the underlying application. So then that's great, but you might think back to the previous slide and be thinking of some challenges that might exist if you're injecting a sidecar everywhere, right? So one of the challenges is transparency. So in order to be part of the mesh, you need to inject the sidecar container. So when you inject the sidecar container, that means the application has to restart. So any CVEs or any like updates that you have to make involves the application restarting. And that's especially complex for short-lived workloads like Kubernetes jobs. It also is challenging to do incremental adoption when you're first adopting a service mesh. So sometimes users don't actually want the full feature set of a service mesh. They only care about a specific feature like MTLS. So you don't really need the whole like L7 policies that exist in Envoy. But because you're injecting that whole Envoy proxy as the sidecar, it's you might not be using all the features, but you still have to do it. And that adds additional overhead costs. So you need additional resources allocated to inject the whole Envoy, and then you're paying more money for features that you're not using. So those are kind of two challenges that led to Istio adopting a new mode. So sidecars are still supported. They will always be supported. But for the use case where you want only a specific feature set and you're more cost conscious, there's a new mode that Istio has called Istio Ambient. This splits up the L4 processing and the L7 processing into two separate proxies. So there's the Z tunnel, which is a daemon set that's co-located with the app on the node. And then this only is responsible for L4. So it will be responsible for MTLS and any authorization policies that don't require L7 config. But if you do want L7, you can still opt in. So you can create, using the Gateway API, a waypoint that is still the Envoy proxy, but you scope it to either per namespace or per service account. So it scales slightly better than having a sidecar Envoy injected everywhere. So it's also leads to incremental adoption rate, because not all of your apps might need L7 policies. So you can choose which use cases require L7, which use cases require L4, and it scales slightly better in that way. So those are kind of the two parts. The L4 part is the Z tunnel, the zero trust tunnel, and then the L7 part is the waypoint. So how does this magic work? So I kind of glossed over another component that Istio now has, the Istio CNI. So the Istio CNI is also a daemon set that is also co-located with the Z tunnel per node. So when you label your workload as being in ambient mode, so like you label the namespace as being in the ambient mesh, right? The CNI pod will jump to the workload network namespace and change the IP table rules to send traffic to the Z tunnel. So it sets up those redirection rules, and then it notifies the Z tunnel that it needs to create a workload proxy. The Z tunnel pod that's the daemon set again that's running per node. It'll create the listening sockets inside of the workload namespace, and then subscribes to any Istio CNI events that happen later. So there's actually a great doc on the Istio website that kind of explains the traffic redirection and how that works. A lot of different CNIs are supported, so Calico, Cilium. I'm going to just use the default one that came with this installation, but you can change in and out the CNI here. Cool. Okay, so then how does identity work in Ambient? So we kind of took a look at how the sidecar was handling identity. Ambient mode is very similar. So your Z tunnel, your zero trust proxy, tunnel is zero trust tunnel. The L4 proxy is what's assuming the identity of the pods running on the same node. So each service account has its own identity. And then the Z tunnel is what's still doing the CSR request to IstioD, and then IstioD is still returning the signed certificate for the workloads being impersonated. So you still have that data plane control plane divide. IstioD is still doing the cert rotation and all of that stuff. Cool. Okay, so now we're going to take a look at how to do the previous demo where we did our surgery to edit our app to include the certs, the easy ambient way where we don't have to do any of that. Again, this is the same link as before, just slightly different section in the steps. So in the MTLS, the easy way, we're first going to label our default namespace. So to recap, our default namespace now has our client and server, the first demo that we did where there was no encryption, and our MTLS client and server. But I'm going to show how the unencrypted, unsecure client and server can still speak MTLS with ambient. So let's label that default namespace. This is the key magic. This is what the CNI is looking for, right? So once I've labeled that, let's send some traffic. So just to make sure that it worked, right? So I send a request, I get it back. Again, I'm using HTTP as before. So now we're going to try to prove that this is actually using MTLS. So I'm going to send a bunch of traffic, leave that happening here, and then look at Prometheus. So let's open a new tab. Oh, nice, I even have it up. Cool, and then I always forget, it's like Istio TCP, is it received? Yeah, let's look at received. Received, okay. So I'm gonna run a simple Prometheus query. So a nice thing about Istio is the observability that you get. So you get all of these metrics for free once you're in the mesh. So this is one of the metrics that we're getting from the Z-tunnel. Because the Z-tunnel is only L4, we're not getting L7 metrics. We're only getting L4 TCP bytes received, right? But we can see that this is a metric we got where our destination is the server. Our source is, this is the SPIFFE ID for the client, and the source workload is the client. And then the most exciting part is our connection security policy is using MTLS. So we've kind of proven that even though we're sending an HTTP request, it goes to the Z-tunnel, gets captured, and we use MTLS. Cool. So then the next thing we're going to do is look at the same thing in Kiali. So Kiali is another open source project that lets you visualize the traffic graph. So if I go to the traffic graph section and I enable security and the traffic animation, because those are fun, I can see that my curl request is still sending from the client to the server, and I am using MTLS. So MTLS is enabled. Here are the SPIFFE principles that we have set. Cool. So the last thing I wanted to point out is you can still use istio-ctl to debug the Z-tunnel. So you can see which workloads the Z-tunnel knows about using Z-tunnel config workloads. So this is like a nifty istio-ctl tool that shows what are the things that the Z-tunnel knows about. And then for a specific Z-tunnel, you can also see the certificates. So I always forget which one it is, but let's try this one. If we look at a specific Z-tunnel, we can see what are the TLS certificates that it's holding. So it receives, again, remember TLS, it receives a cert from the control plane, and then these are what the Z-tunnel is using for MTLS. So we can see that our client is here, and here's the server. Yeah. Cool. So the last thing I wanted to show is you might think like, okay, so now you're using MTLS, but before in our manual example, we actually restricted it to only allow the client server to talk to the server. Right now, like everything is our communication is using MTLS, but we don't have that restriction in place. So it's not really zero trust, right? But luckily, Istio provides policies that you can use to restrict who has access to what. So one of the resources that Istio has, the CRs, is called an authorization policy. And if you put this policy in the Istio system namespace, that means everything in the mesh is having this policy applied. And we're going to just deny all. So we're going to apply this deny all policy, which means that nothing in the mesh can talk to each other unless it's explicitly allowed. So when I apply my deny all policy, then send some traffic, I'm expecting this not to work. So yep, so we get our command terminated with exit code 56. So our connection from the client to the server isn't going through because our deny policy is in place. But we can still grant permission, based on zero trust principles, to only grant our client to be able to talk to the server by creating another authorization policy that allows our client to talk to the server. So we're going to have an allow action allow. We're going to match the server, and only this service account will be able to talk to the server. So our client service account that we looked at earlier in the Kubernetes manifest, this is the only thing that will be able to talk to the server. Cool. So let me apply that. And then let's send the same request as before. Let me just go back. I don't feel like copying. Yay. So we get our response back. We're still using MTLS, and we have our authorization policy in place to make sure everything's actually locked down. So that's all I had demo-wise. If we go back to the slides, and also feel free to check it out on your own. Lynn had some other examples with an L7 policy in her demo at Cloud Native SecurityCon that are also included in this repo, so feel free to check those out. But some key takeaways to summarize: Zero Trust is a security framework that assumes no workload should be trusted by default. Kind of boils down to this cute saying, never trust, always verify. Some benefits of Zero Trust that we looked at: it reduces the attacker's surface. So an attacker can't move as freely within the network. And it also enforces continuous security validation and secure communication between all the entities in your network. We looked at the hard way of achieving Zero Trust, where you have to manually manage the certs and create the certs and like do surgery on your app to actually get the certs to be used. An easier tool that exists to achieve Zero Trust are service meshes. So I know service meshes are like everywhere. They do a lot of things, but security is another thing that they do very well. They provide MTLS between workloads because your control plane is handling the cert rotation for you. And that allows you to have secure policies like the authorization policy we looked at to lock everything down and restrict service-to-service communication. And I think one of the cooler things that Istio provides is you don't need to change any of the underlying application code. You just need to label a namespace, and it's like magic. It works. Especially with the ambient mode, there's no even like application restarts. It just the traffic gets redirected and it goes through the Z tunnel, and you get MTLS. So if you're interested in learning more, the Istio docs have great documentation on different security concepts. So how Istio manages the identities like we looked at. There's also a new Istio ambient doc. So ambient is right now in beta, but they're targeting GA for the next release. So it's been around for 2 years now, but if you want to try it out, the docs are pretty up to date and a good guide to getting started. There's also a lot of security policies we didn't get a chance to talk about. So peer authentication, request authentication. We touched on L4 authorization policies, but you can also do L7 authorization policies. The Istio docs, again, have great examples on how to use JOT tokens and things like that. And then I'd also like to thank Lynn for her help with this talk and helping you create the initial version of the demo. She, again, gave this talk in like 15 minutes at Cloud Native Security Con, and I thought it was really cool. So I also encourage you to check that out and try out the demo yourself. So yeah, thanks everyone. That's all I had. I guess we have a couple minutes for questions maybe.
Thank you so much, Nina. I mean, that was so insightful to see, the hard way of doing security, and as well as the kind of an importance that it carries. So these 9 days that we are having, the kind of podcasts that we are having right now, they are mostly centered around cloud and security and some other parts of tech. So we really believe in good over evil, especially during this time of the year, during the festivities, and also I think security plays a very, very important part in that whole discussion about tech. Um, Thanks everyone for joining. If you have any questions, make sure you pin it down, or you can. I think you can even unmute and ask Nina directly.
Yes, speaking of upcoming talks, I'll go back to the slide. There is an actual service mesh talk coming in. Again, like we didn't really get a chance to dive into all of the aspects of service mesh. It's mostly focused on security, but I would highly encourage you to go to that one as well.
Sure. I really hope everyone took some key takeaways from here for sure. And I personally would be very much interested in trying out this demo for sure. Thank you, Nina. Thank you so much. It was a great session.
Thanks, everyone. I'll stop sharing.
Thank you, everyone, for joining. Thank you.
Great. Thanks, everyone.
Thank you, Ravani. Thank you so much for promoting this. She's been doing most of the work these days, as the rest of us are kind of running busy, but she is like so dedicated. And Women in Cloud Native, I think she holds a very strong foundation of it. So thank you, Ravani. Thank you for helping us host this entire thing. Ravani, you are on mute if you're talking. Okay.
I think she also had a conflict, so yeah.
Okay. So are we good to wind up, maybe? Okay. Thanks, John. Thanks, everyone, for joining. Thank you, Nina, once again for joining us. See you soon. Bye.
Bye.